Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about gas-forming reactions. And when I talk about this, what I mean is reactions that produce gaseous products. So far, we've mostly been looking at reactions that produce solids, so think precipitation reactions, liquids, such as the water that's formed in acid-base reactions, or aqueous products, such as, well, any of the reactions we looked at, whether it's precipitation, acid base, or redox. Most of these will perform aqueous products. However, sometimes we form gas products. So think about the classic elementary school reaction of mixing vinegar or acetic acid with baking soda, also known as sodium bicarb. So sodium bicarb. When you combine these two, the acetic acid becomes acetate, and that bicarb breaks apart into water and CO2 when it gains a proton. So one of the reasons why these gas-forming reactions are very important is they tend to take mass out of the system, and this helps prevent any reverse reaction. So it's very hard to react CO2 and water to reform bicarbonate. You have to be very patient to make that work. And as a result, it's a very good way to make sure that reactions proceed in one direction and you get very good yields. Also, it turns out that it's a good way to monitor the course of a reaction. You can be sure a reaction has taken place if it's produced the gas. And you can also even do this more quantitatively. You can actually, say, put a balloon over your vinegar volcano and see exactly how much of that CO2 you've generated, which gives you an idea of how much of the acetic acid reacted. And as a result, you'll occasionally couple gas-forming reactions with non-gas-forming reactions to take advantage of one of these two uses. It also turns out that most of these gas-forming reactions typically take place when you expose a chemical species to either an acid or a base. And this produces four of our more common gas-phase products. Sulfur SO2, sulfur dioxide, which is a greenhouse gas, as is carbon dioxide. We also have hydrogen sulfide, which is that characteristic smell of a rotten eggs. And we have ammonia, which is that very sharp smell that you get off of Windex. And all of these are involved with certain reactions. So for example, you can go ahead and form sulfur dioxide out of sulfites. Carbon dioxide is produced when you react either carbonate, as such as found in limestone, or or bicarbonate, such as in baking soda, with extra acid. You form carbonic acid, which then splits apart. Similar, you can end up reacting sulfide with hydrogen to form hydrogen sulfide. And amine is often present in aqueous systems as its acidified version of ammonium. So let's go ahead and take a look at where you might find some of these origins of these gaseous species. So for example, CO2 is often produced from calcium carbonate. So if you react limestone with acid, you produce carbon dioxide. Sulfides are often found in things like iron sulfide, so this is pyrite or fool's gold, or nickel sulfide, which is found in a lot of other metal ores and is a source of a lot of nickel mining. However, a lot of these you'll find in nature, such as sulfites. So if you ever hear about people getting hangovers from wine, one of the reasons why is wine tends to have high levels of sulfites, which reacts badly with some people's metabolisms. And again, ammonium is found in all sorts of aquatic systems and is a predominant way that nitrogen is moved from one organism to another to help make proteins. And again, all of these will naturally degas under either acidic conditions for most of these species or basic conditions if we're looking at ammonia. So one of the big things to be very aware of with gas-forming reactions is if you're working with an acid-base reaction, be very aware that if you have an ion, which is based on sulfite, carbonate, sulfides, or ammonium, because when you react these species, I have to be very aware that the species will break apart and produce water as a byproduct, as well as a gaseous species. However, these reactions also are involved in a lot of other very important processes. So one example of a classic gas-producing reactions is metal sulfide ores. So one classic example is copper sulfide. So a lot of good copper ores were long ago extracted. So one of the predominant forms you'll find copper in mines these days is as copper sulfides. And the easiest way for miners to extract that copper is by reacting with sulfuric acid, which is one of the cheapest acids you can find. So when this happens, you go ahead and you protonate that sulfide. It immediately leaves the system, though be very careful because hydrogen sulfide is toxic at high levels, which makes this type of mining a little dangerous. And the byproduct is copper sulfate, which is a dissolved species, and you can then use redox chemistry to isolate that copper to form metallic copper. But one of the reasons you have to be very aware of these processes is thinking about what else may be happening. And when you introduce this much acid to a system, it's very possible that this extra acid from this type of acid mining can leak into the environment and can really harm the system. And what you see here on the right is an example of a stream that received a high level of runoff from an acid mining site, which contains a lot of metal ores because it's dissolving all of the metal carbonates and sulfides that exist in the environment. And so it's a quick way to end up with a polluted system. And this is one of those areas of current argument amongst industrialists versus environmentalists. Is it worth pulling out these metals with acid mining, or are we doing too much damage to our environment? So next time, we're going to be prodding the behavior of our gases a little bit more in detail. One of the big advantages of this is by understanding our gas behavior much better, we can understand our gas forming reactions, which help monitor what's happening in solution so much better. So until then, take care.